In the last video, we looked into an Irish dataset where using LSTM network, we would write few words or predict next few words of the song. Thus, in the end, we found that the number of lines or the sentences of the songs were not too much and which led to overfitting where we got the training accuracy above our validation accuracy. So this time we'll be extending our data set. The same pattern that we use to hardcode data set can be extended to use the text file very simply. So the author has hosted a text file containing about 1700 lines of text gathered from a number of songs that you can use for experimentation. With a little modification, you can use this instead of single hard-coded song. Right, so there are a number of songs whose sentences are provided to us as a form of dataset. So it's simple, you just get that data set that's hosted. You get it using wget, no check certificate and the link. And simply we open it, we read it, we get the corpus. First we have to convert all into lowercase and split it with \n. And once we have opened it in the read format, we'll see that the rest of the things go as it is as before. So I hope you have the code from the last video that we had hosted before. But if you don't, just feel free to go about it and have a look at it. I'll link it somewhere in the above or in the end. So from that we see that the training of this for about 1000 epochs brings you about an accuracy of 60% with flat curve flattening out. So you can see how the accuracy is increasing till 60%. Try the phrase in the town of Athi again yields the prediction of 1. But this time with only 40% probability. For Sweet Jeremy saw Dublin, the predicted word is dawn with probability of 59%. And the next 10 predictive words are here. So it's looking a little better, but can we improve it further? For improvement, let's make a few changes here and there in our model architecture. So one way we can improve the model is change its architecture using multiple stacked LSTMs. So we have already heard and learned about multiple or stacked LSTMs where we use multiple layers of LSTMs in our model architecture. So as you can see that firstly we have an embedding layer, then we have bidirectional LSTM layer, and in the next we also have added another bidirectional LSTM layer which gets the parameters of maximum sequence length minus 1. Right, the next all things go similar as before, for we fit the model for around 1000 epochs. So you can see that impact of changing or adding a stacked version of LSTM, one more layer of LSTM, you can see there is some change in the graph that we have seen before. We see a lot more hinges here, right? So when tested the same phrase as before, this time we got more as the next word after in town of Athi with 51% probability. And after Sweet Jeremy saw Dublin, I got Kaylin, so the Gaelic word for girl, with 61% probability. Again, when predicted more words, the output quickly descended into gibberish. So he's given few examples as well. If you get different results, you don't have to worry. You didn't do anything wrong, but the random initialization of neurons will in fact impact the final scores. So how can we improve our data? We see there is some kind of things that we need to change or improve in our data so that we don't get into those nonsensical outcomes that we are getting right now. So there's a small trick that you can use to extend the size of the data set without adding any new songs. That's called windowing the data. So right now that every line of song is single line, And when tuned into input sequences, we get figure 8-2. Yeah, here. So you can see over here that what the windowing actually means is. So like in the town of Athi is one window, and it can be further divided into number of lines. So first in, then in the, then in the town, then in the town of. So that's how you can increase the amount of data set or the number of sentences. Right, let's read ahead. It says, while humans read songs line by line in order to hear rhyme and meter, the model doesn't have to, in particular when using bidirectional LSTMs. So instead of taking the line in the town of Athi, one Jeremy Langian, processing that, and then moving the next line and processing that, we could treat all the lines as one long continuous text. We can then create a window into the text of our n words, process that, and then move to the next window. So what it's saying that we should not take the whole data set as a set of lines or set of sentences. Instead, we should take the whole data set as one big line, and where we can just divide it into number of windows, right, for n words. So as we have seen here. So the window would move one by one according to the stride given to it. In case far more training data can be yielded in form of an increased number of input sequences. Moving the window across the entire corpus of text would give us this input sequence. So that's the size of input sequence that we could train with, right? So that is input number of words minus window size multiplied by window size, right? So let's just come down to the code now. So we have selected the window size to be 10, means 10 words would fit in one window. Then sentences, there is list of sentences and all text. We read the data, we lower it down, we convert it into lowercase, we split it, and then we get the range size, what would be the range, so that our window won't end up having less number of words in the window than defined, right? So there's a loop then. So what are we going to do is we're going to get the words and just append it into the this sentence, and finally we'll get our window. In this case, because we no longer have sentences and we're creating sequences the same size as moving window, maximum sequence length is the size of the window. The full file is read, converted to lowercase, and split into an array of words using string splitting. The code then loops through the words and makes sentences of each word from the current index up to the current index file of the window size, adding each of these newly constructed sentences into the sentences array. Then, when training, you'll notice the extra data makes it much slower per epoch. So when you have extra data, of course, the number of epochs, it doesn't matter, it would be slower. But the results are greatly improved. So, and generated text descends into gibberish much more slowly, right? There are many hyperparameters that you can try tuning in order to reduce the overfitting. So changing the window size will change the amount of training data. A smaller window size can yield more data, but will be few words to give to a label. So if you set it too small, you will end up into a nonsensical poetry. You can also change the dimensions in the embedding and number of LSTMs or the size of vocab to use for training. Given that percentage accuracy isn't the best measurement, you'll want to make a more subjective examination of how much sense the poetry makes. There is no hard and fast rule to follow to determine whether your model is good or not, right? So, for example, say the author has tried a window size of 6, right? So increasing the number of dimensions for the embedding to 16, changing the number of LSTMs from window size, and upping the learning rate on Adam optimizer. I got a nice and smooth learning curve, so he shows us the learning curves that he got, so you can see the accuracy he got, right? So then he got this poem. Then yeah, you can see the poem, right? So I am no big Irish poems fan, so I really don't understand these kind of poems. But I hope if he got a good accuracy on that, it would not be such a nonsensical poetry in short, right? While the phrase "whack-foe" may not make sense to many readers, it's commonly heard in some Irish songs, like kind of like "la la la" or "dooby dooby doo." So, what I really liked about this is that how some of the later phrases kept some kind of sense, like "such power of her good and her gear and her calypso blood." But this could be due to overfitting of the phrases that already exist in the song within the corpus, right? So it's many times you have seen that there are times when the words already exist in the corpus and we get good accuracy on that. But when we actually work on or get the something line to predict upon that the model hasn't seen before, it usually gives us few words correct, but usually the whole sentence doesn't make any meaning, right? So if you encounter issues like that, it's best to reduce the learning rate and may decrease the number of LSTMs. But above all, experiment and have fun. So, what if we don't want to go for word based encoding? We want to go for character based encoding. So, there might be many words. So, the words in the dictionary are endless. So, what if we just encode the characters? So, there are less unique words, less unique characters, I would say, as compared to the words. So, as such, you have a lot few neurons in your output layer, and your output predictions are spread across fewer probabilities. So, it's a good idea actually. So, when you look at data set of complete works of Shakespeare, you'll see that there are only 65 unique characters in the entire set. So, when you're making predictions, instead of looking at the probabilities of words across 2,700 words, as in Irish songs, you are only looking at 65 new characters, right? So, it makes your work a bit easier. What's also nice about the character encoding is that punctuation characters are also included, so line breaks, etc., can be predicted. As a result, when I used RNN trained on Shakespeare corpus to predict the text following on my favorite Game of Thrones line, I got this. So you can see that it's a huge lines that he got. And it's kind of cool that she identifies him as traitor and wants to tie him up. So I have no idea what this is going about, but I can surely think from the outcomes that we've got that it was far more better and easier to do character encoding as compared to word encoding, because obviously the number of unique words are more than the number of unique characters in the world. So, as this model works well for us, we can still play around and tune some of the hyperparameters like learning rate and all. But in the end of this chapter, we can say that in this chapter we explored how to do basic text generation using trained LSTM based models. You saw how you can split the text into training features and labels using words as labels and create model that when given seed text can predict the next likely word, right? So you iterated on this to improve the model for better results. Exploring a data set of traditional Irish songs, you saw a little about how this could be potentially be improved using character-based generation and with examples from Shakespearean text, right? So in the next, what we'll be doing is we'll be understanding sequence and time series data. So we know that time series is everywhere, be it stocks, be it temperatures, weather forecasts, and historic trends like Moore's law. So time series is everywhere, and how we deal with that using machine learning and artificial intelligence, we'll look into that in the next video. So till then, do check out the code of this whole chapter 8, and I hope you understood well about LSTMs, RNNs, and I hope to see you in the next time. Thank you.